Hey everyone, in this video we're going to be talking about tensors, which are the building blocks of machine learning. So what are tensors? Tensors are fundamental mathematical objects used in various fields, including physics, engineering, and machine learning. In simple terms, a tensor could be a few things: a vector, which is an array of numbers, a matrix, which is an array of numbers, and they can be even higher dimensions, so they can be 3D matrices, 4D matrices, 5D matrices. For example, a 3D matrix would be an array of arrays of numbers. So tensors are especially important in deep learning, where they represent the core data structure for neural networks. Let's understand this by breaking down the concept of tensors by dimensions. So a scalar, which is a zero-dimensional tensor, is just a single number. So here we're importing NumPy, we're creating an array with an element 5, and this isn't even actually an array because we don't have the brackets here to signify that it's an array. It's just the element 5, but we're creating it with the array function. So the shape should be empty because there's no array. And here we go, we can verify that the shape is empty. This is how NumPy represents it. So next, let's move on to a vector, which is an array of numbers, which is a one-dimensional array, one-dimensional tensor. So if we run this, what we should see is that the shape is 5 because it's an array which contains 5 elements. Here we go, you can see that the shape is 5. Now moving on to a matrix, which is a two-dimensional tensor. It's a two-dimensional array of numbers. It's an array which contains 3 arrays, which means that the shape should be 3, 3. Why? Because it contains 3 arrays which each contain 3 elements. So the shape should be 3, 3. And here we go, we can verify that the shape is 3, 3, and hopefully that makes sense. Now for higher dimensional tensors, because tensors can have more than 2 dimensions, for example a 3-dimensional tensor could represent a cube of numbers, here we should see the shape is first an array which contains 3 arrays, each of which contains 2 arrays, and each of those arrays contains 2 elements. So the shape should be 3, 2, 2. And we can verify that the shape is indeed 3, 2, 2. Now let's talk about tensors in machine learning. In machine learning, tensors are used to represent various types of data. Input data, which are images or text or so on. Model parameters, which are weights and biases. And intermediate representations in neural networks. So let's create a simple example using PyTorch to demonstrate how tensors are used in a basic neural network. So here we're importing PyTorch. We're creating a random input tensor with a shape 3210. So it'll generate a bunch of random numbers with in an array which contains 32 arrays, and each array contains 10 elements. Here we're defining a simple neural network with a first layer containing 10 inputs and 5 outputs, and the second layer containing 5 inputs and 1 output. The first layer having an activation function of ReLU, a rectified linear unit. And if any of this is not making sense, for example, what is ReLU, what is a linear layer, what is a neural network, I've made a video on what neural networks are and how to code one out using PyTorch. So all this code should become understandable to you, if it isn't already, once you've watched that video. So be sure to watch that video, and this as well as other code that we're going to go over in this video will become much more understandable. So we're creating an instance of the model here, and then we're passing the input tensor through the model to generate an output. The input shape should be 3210 because that's what we're saying the input tensor should be. And then the output should be 32.1 because we have 32 as the batch size and 1 output. So if we go ahead and run that, we should see that the input shape is indeed 3210 and the output is 32.1. So in this example, we created a random input tensor with 32 samples and 10 features each. We then defined a simple neural network with 2 linear layers, and we passed the input through it. The shapes of the tensors change as they flow through the network. Understanding tensor operations is crucial for working with neural networks and other machine learning models. Common tensor operations include reshaping, element-wise operations, matrix multiplication, and reduction operations such as sum, mean, and so on. Element-wise operations could be addition or subtraction, and so on. Here's a quick example of some tensor operations. Here we're creating a tensor with a shape 2, 2, and we want to reshape it to a 1D tensor with a shape 4. That's possible. We can actually do that by using the reshape function. So this 1, 2, 3, 4 will become 1, 2, 3, 4, but as a 1D tensor instead of a 2D tensor. Next, we can do an element-wise multiplication of A, multiplying each element with the number 2. We can also do a matrix multiplication of A with itself. So what a matrix multiplication is a dot product. And what's a dot product? An addition of multiplications. So we're taking the dot product of each row with each column. So the element in the output tensor is going to be 2 by 2. The element in the first row and the first column is going to be the dot product of the first row and the first column of A. So here I have a demonstration of what that looks like. 1, 2, 3, 4, which is A, multiplied by itself, a matrix multiplication. We multiply the first row with the first column to get the element in the first row and the first column, and so on for the rest of the rows and columns. And this is going to be the output tensor. This element of the first row and the second column is going to be the dot product of the first row and the second column. The second row and the first column is going to be the dot product of the second row and the first column, and so on. And here we have a reduction operation, in this case just a sum, which is going to be a sum of all elements. So if we print this, we're going to see that that it's been reshaped to a 1D tensor with the shape of 4. And we have an element-wise multiplication, multiplying each element by 2, 1 times 2, 2 times 2, 3 times 2, 4 times 2, which becomes 2, 4, 6, 8. And we have a matrix multiplication, which, as the demonstration showed, the output is 7, 10, 15, 22, and the sum of all elements, 1 plus 2 plus 3 plus 4, which is equal to 10. Now let's talk about tensors with gradient information. In addition to storing data, tensors in deep learning frameworks like PyTorch can also track gradient information. So what's a gradient? A gradient is how much does a change in one value affect another value. And in machine learning, the other value that we usually want to track is the loss function. It's the error function. We want to minimize the loss function or the error function. So we want to figure out how does it change in the weights and biases of the neural network of each neuron affects the loss function. So we know how much to change it when we do backpropagation. So again, this capability is crucial for implementing backpropagation, the algorithm used to train neural networks. When a tensor is created with requires grad equals true, it tells the framework to track operations performed on this tensor and compute gradients with respect to it. This is particularly useful for model parameters, weights and biases, and input tensors that require gradient computation. Though gradient computation is usually used only for weights and biases and not for the input. So let's demonstrate this with a PyTorch example. Here we're creating a tensor with gradient tracking because we're setting requires grad equals true. So when we print x, we should see the tensor 1, 2, 3, 4, and when we print this requires grad, we should see true. Now we're performing some operations. We're taking the power of 2 for each element. So 1 to the power of 2 is 1, 2 to the power of 2 is 4, 3 to the power of 2 is 9, 4 to the power of 2 is 16. And we're taking the sum of all of them. So 16 plus 4 would be 20, 9 plus 1 would be 10, and 20 plus 10 would be 30. So y should be 30. Then we're computing the gradients. And here, by doing x dot grad, we should be able to find the gradients of x after doing y dot backward, because we're computing the gradients with respect to y. So here we go. We can see that the gradients are 2, 4, 6, and 8. And the reason why is because in calculus, the gradient is just the derivative. And the derivative of x squared is 2x. We have something called the power rule, in which we just bring down the power. So x squared becomes, when we take the derivative, it becomes 2x. So the gradient tensor would become 2x. So 2 times 1, 2 times 2, 2 times 3, 2 times 4, which becomes 2, 4, 6, 8. So in this example, we created a tensor x with the required gradient equals true. We performed operations on x to create y. We called y dot backwards to compute gradients, and the gradients are stored in x dot grad. The extrograd tensor will contain the partial derivatives of y with respect to each element in X. This is the essence of automatic differentiation, which is key to training neural networks. Let's expand on this with a more practical example involving a simple neural network. So here we're creating a really simple data set, 1, 2, 3, 4, 5, 6. That's all. Not a huge data set like most machine learning problems require. And then a really simple output, 3, 7, and 11. We're creating a simple neural network with a linear layer of 2, with an input of 2 and an output of 1, and no activation function. Then we're creating an instance of the model. We're setting the loss function, mean squared error loss. The optimizer, which is stochastic gradient descent with a learning rate of 0.01. And again, if this doesn't make sense to you, what is a loss function? What is an optimizer? Be sure to watch the video that I made on neural networks, and this will make a whole lot more sense. Here's our training loop in which we do a forward pass and then a backward pass with optimization. And once it's all trained, once our model is trained, we should have the model parameters, the weights and the bias, as well as the gradients here when we print them out with param.data and param.grad, because we're doing name and param in the model name parameters. Then what we're going to do is we're going to make a prediction with gradient tracking so that we can find the gradient of the input and see how this behaves. So let's go ahead and run that. So as you can see, it ran in under a second because it's a really simple data set, just 1, 2, 3, 4, 5, 6. And here we have the parameters, the weight and the bias. The parameter of the weight is just the values of the weights. So since we have an input of 2, which is 2 edges, and 1 output, 1 neuron, we're going to have 2 weights, 1 for each edge, and 1 bias, 1 for each neuron. So we just have 1 neuron. So the parameter, again, is just the value of the weight, and the gradient is how much does a change in the weight affect the loss function. And it's the same for the bias. The parameter is the value of the bias, and the gradient is how much does a change in the bias affect the loss function. And for the gradient of the input, what we're doing here is we're testing how much does a change in the input affect the output, not the loss function, the actual output. You'll see that it matches the weight. And why is that? It's because the output is just the input times the weight plus the bias. So the change in the input is going to be multiplied by the weight, which is why the gradient of the input, the change in the input, is just the values of the weight. This example demonstrates several important concepts. First, we create an input tensor x with requires grad equals true to track gradients through the entire computation graph. Then the model parameters, the weights and biases of the linear layer, automatically have requires grad equals true. We don't need to set that. During training, we compute the loss and call loss to backwards to compute gradients for all tensors in the computation graph that require gradients. Then the optimizer uses these gradients to update the model parameters, and after training, we can inspect the gradients of the model parameters. We can also compute gradients with respect to input tensors as shown with the X-test. Understanding how tensors track gradient information is crucial for implementing custom neural network layers, debugging backpropagation issues, implementing advanced optimization techniques, and analyzing model sensitivity to inputs. This gradient tracking capability of tensors, combined with automatic differentiation, is what makes modern deep learning frameworks so powerful and easy to use. In conclusion, tensors are versatile mathematical objects that form the foundation of modern machine learning. They can represent data of various dimensions, from scalars to complex multidimensional arrays. In deep learning frameworks, tensors not only store data, but also track gradient information, enabling efficient training of neural networks through backpropagation. Understanding tensors and their operations is essential for anyone working in the field of machine learning and artificial intelligence. So if you have any questions, leave a comment below. If you liked the video, be sure to leave a like, and to stay tuned for any future content, be sure to subscribe. Thank you for watching. Cheers.